going to go ahead and get started. So it's my great pleasure to introduce Pratik Chaudhari. So as many of you know, Pratik is a new professor here in the ESC department. He's been with us a little bit less than a year. He did his PhD work with Stefano Soato at UCLA. And then where he actually did a lot of great theoretical work to understand the sort of the unreasonable success of deep learning training methods. And he was able to formally improve some really important results about the nature of the regularization afforded by a stochastic gradient descent. After he did his PhD, he spent a year as a postdoc at Caltech and also as a senior applied scientist at Amazon. And before that, he also worked as a principal engineer at Nutonomy, where he worked on actually bringing self-driving technology to market. So again, one of the really great things about Pratik is he brings not just this great deep theoretical understanding, but also an engineer's perspective on how you can actually go about bringing those tools to bear on actual problems. So it's really, really fantastic to have him as part of the GRASP laboratory, and we're looking forward to hearing his talk. So take it away.
Wonderful. Thank you so much for a very, very kind introduction. I don't believe I could have introduced myself any better. Let's begin. So actually, before I begin my actual talk, I wanted to show some of the things that we've been doing during the, can you see my screen? Can you see a video on the screen? So the last 1 month or so has been pretty difficult for most of us. We are stuck up inside our houses, trying to reason about what to do. This is a video that was created by Sherry Chen. She's a master's student in CIS. And she has been interested in looking at interaction of vehicles on the road. How should a driver, an autonomous car in this case, kind of engineer the environment around it in order to make decisions. So oftentimes you may have noticed that you come to a four-way intersection and then each of us is waiting for the other car to make a move. So we would like autonomous cars to be better at handling these kinds of situations and kind of give us the same behaviors that we have become accustomed to as human drivers. Nudge the car a little forward if you cannot see something, force people to move a little faster if you are in a hurry, so on and so forth. So I'll kind of walk you through this video. She has created this demo where each of the little blue boxes are cars that are simulated. These cars are simulated with a slightly non-trivial driving logic, so they keep going forever in this little arena. The light blue car is the car that is driven by a reinforcement learning agent, which has learned to kind of take all these blue cars around it in its vicinity as input, and then learn a behavior where we can tune the aggressiveness of the light blue car modulo the driver aggressiveness of the other blue cars. And this agent has now learned to drive both in a safe way. So it comes close to the blue car, but then it brakes, as you can see here, in order to not hit it. And the cool part is that it understands complicated interactions of this form. So this particular car right now is heading forward, whereas this car could be heading forward or could be coming out of the intersection. And this little blue car has understood that it has to wait before it makes a decision as to whether to proceed or not. So this is what Sherry has been up to over the last 1 month. I wanted to show it as a example of what students have been doing as they are sitting inside their homes and not just watching Netflix. But let's now begin with the rest of my talk. Today's talk is about how to do machine learning when you don't have a lot of data available, but you have few data available. And we'll be looking at two specific problems in this arena. The first one is what is called few-shot image classification. And I'll tell you what it is in a bit. The second topic of this talk, it will roughly be split in 30 minutes each, is what I call a thermodynamical perspective of representation learning. We're trying to formalize what problems like transfer learning, few-shot learning, continual learning, lifelong learning look like. And we would try to build an information theoretic understanding of these concepts. So to motivate few shot learning a tiny bit, there are really three different regimes of image classification that we've become good at today. The first one is what we would call the high shot regime, in which case you're given maybe about 1,000 images per class, and these classes could be cars, cats, dogs, planes, all the things that you and I have become used to looking at. Roughly speaking, we are good at solving these kinds of problems. If you give me even 1,000 classes with 1,000 images each, this is the data set called ImageNet that you have heard many times before. We have become good at building image classification systems for such data sets. What we are not very good at yet is what is called the low shot regime, where let's say there is a farmer in California who grows 3 different kinds of strawberries on his farm. Now, he would like to build a machine learning model to classify these 3 kinds of strawberries. He's really not interested in how well you classify cars and cats and dogs. He may be willing to give you some data. He doesn't understand why you need data if you're such a good computer scientist. So he gives you 5 samples of these strawberries. Maybe if you ask him nicely, he may give you 25, but not more than that. So there's an order of magnitude difference in the kind of number of samples we get per class on these problems versus the cars and cats. And I would like you to appreciate the fact that there are millions of low shot problems. So as a machine learning kind of enters newer and newer domains, I would like to do something with machine learning in my house. I may not be an expert, but I have some data and I would like to do these strawberries. Someone else grows cucumbers on these farms and they would like to do the same. There are millions of people who would like to build these models. They don't necessarily have the expertise or the know-how. And we would kind of want to create these, take these good algorithms that we've designed in the high shot regime and then translate them into the low shot regime. The next case is, of course, the extreme low shot regime. Let's say I go to a rainforest, I find a new beetle, and I'm really doing anomaly detection at that point of time. Is this beetle different from what any other person has seen on this planet? These are problems that we haven't even started to look at, and they may be down the future. If you are into robotics, I am. You could consider a canonical example of this form. Let's say I buy a robot manipulator from Amazon, and I would like to do certain kinds of tasks with this robot manipulator. Today, we are interested in solving tasks of this form. So maybe I want to learn how to pick up cups. Maybe I want to learn how to pick up a soccer ball with this arm, maybe a bottle of milk. And I may want to generalize across many different objects. Because if I see a lot of objects and practice very hard, I may be able to handle models, create models that work on slightly different kind of objects. It is more about handling different objects. There is a complementary view of looking at these transfer learning problems, and that is as follows. So a robot that you bought at home is very different from the robot that Tesla has on its assembly line or any other company has in its factory. And what you want to do is really transfer models that you learn on supervised data or collect data that you collected at leisure in your house onto these kinds of models. You may be interested in models that transfer across different sensors. So a model that has 6 cameras, now one of them conks off. You may be interested in working with only 5 cameras. Your policy has to be robust to these kinds of changes in the sensors. You may want to think about what happens when the gears of my robot start degrading. I'm really doing adaptive control at this point, adaptive control circa 2020, circa machine learning put inside it. So there is different tasks on the left-hand side. There is different situations on the right-hand side. And you want policies that transfer across both of them. And these are some of the problems that we've been looking at. I'll take image classification as the main example in this talk. Mostly because it is very easy to appreciate. There are not too many moving parts as reinforcement learning, but we have been doing some other work in these areas also. There are really 2 main challenges here. So as we said, high shot regime is easy. Low shot regimes are hard for today's algorithms. And the key point, I think, is that you don't really know the regime at training time. Or at test time. So you need one algorithm that works across all these regimes. You don't want to create one specific model. If you give me 2 labeled data, you don't, and this model may not work as well if you give me 1 labeled data. I would like my models to be seamless across what you give me. Let's try to formalize the problem. So you're given a training set. This training set consists of many different tasks. Think of tasks as simply classes, for want of a better definition. These are cats, planes, and dogs. I give you lots of data from these classes because these are easy classes. I can go to the internet, collect lots of images of them. The test task is a task that may not be from one of these classes. It is concerned with new classes, let's say strawberries. I give you W different test classes. So W different kind of strawberries that I'm interested in classifying. And I give you S labeled examples per class. S is what is called the support set in this literature. W is what is called the way, the number of different classes that I'm interested in classifying. Of course, the key point of the few shot setting is that S is very small. If I give you 1 million images of each class, then you don't need to worry about the training set. You simply start training at test time or at the few shot training time and build a good model. If S is just one datum, then there is really not much you can do in order to adapt to this new class. And we'll figure out ways to do this. Let me give you kind of an example, which is and that tells you the flavor of current few shot learning algorithms. Most algorithms are based on what is called meta-learning, and meta-learning is kind of a blanket-all phrase that really captures the specific, the following scenario. I train a bunch of models, a large number of models, and each model is on some specific task. I try to learn one meta model that siphons off information from these base models. And this meta model is kind of a generalist across many different tasks. When I want to solve a new task, I ask the meta model to create a base model for me that is well suited to this new test task. And the meta model somehow understands not data itself, but different kinds of classes, different kinds of tasks. So you should think of meta learning as simply one conceptual step above supervised learning. In supervised learning, you're interested in generalizing across data, across samples. In meta learning, you're interested in generalizing across tasks. And that is also how all the algorithms are built. That is also how all the theory for meta learning looks like. Here is one instantiation. It is an algorithm called prototypical networks. And this is actually a very useful thing to know because it is, you can visualize it very quickly. I collect the meta training set. I collect a large number of related tasks. I train one model on all these tasks. So give me 1,000 classes. I train one model on all these 1,000 classes. But I don't train it merely for classification. I train it for clustering. So if C1, C2, and C3 are 3 different classes, I like all the samples of C1 to be clustered next to each other. I like all the samples of C2 clustered next to each other. So I'm really learning a clustering mechanism, not really a classifier. When the test task comes in, if it is related to the training task, if it is not too different, let's say you collected natural images and you're doing medical imaging, that is a different test task. This won't work well for those kinds of scenarios. But let's say if you collect some kind of a natural image-based test task, then because I've learned a clustering model now, I can ask questions in the test data for this clustering model. It may be good enough to cluster the new data as well. I cluster the new data, and now I have a mechanism for predicting classes of the new data. Because even if I give you one labeled datum from C1, I immediately know that all these green points belong to this label C1. That is how prototypical networks work. So they really combine this one phase of clustering, let's call it the meta training phase, and the second phase, which is more or less of a metric learning phase or a execution of the clustering phase. And this is roughly how most algorithms for image classification, few-shot image classification will look like. Let's see how well they work today. So this is some data that we collected from a few previous papers in this area. The x-axis shows different algorithms. So prototypical networks is the first one. MAML is another very popular algorithm for doing few-shot classification. And the other 3 are also recent algorithms that have been shown to work well. On the y-axis, I'll show what is called the one-shot 5-way accuracy on this data set called MNIST. One shot means that I give you one labeled sample of the new class. 5-way means I give you 5 different classes. And this is a box plot. So the horizontal line here in every box means the median performance. The half width of the box is the 25th percentile of this performance. The problem with few-shot learning that people haven't noticed yet is that the 25th percentile is extremely large. So if I say that prototypical networks has a mean accuracy of 44%, This 44% really comes with an error bar that is as big as 15%, is plus minus 15%. That's really a fact of the universe. Right? The universe has many different few shot tasks, and this is really the variance across all your few shot tasks. So all the while through the literature, we've been comparing the horizontal line of each of these boxes, and we've been saying, look, MAML is like almost as good as prototable networks. Leo is an algorithm from DeepMind. It is a bit better than MAML or prototable networks because the horizontal line is better. We have never realized that the error bars on these boxes are so large. And this is something that you need to really appreciate about what algorithms are we building. So are we really making progress when the horizontal line goes up? Well, yes, to an extent, yes, but not very convincingly. All these algorithms are essentially the same given the data that they're being evaluated upon. Let's talk about the first key idea of this work. And it's a very simple observation. So a classifier that I train on a given dataset, let's call the dataset as DS, is really a function. It's a function f that takes in the test datum x, and then it gives me a label for the test data. In principle, I could take the test datum, the training data, and then search out all these functions f at test time. No one is preventing me from doing it. I will just be utterly slow in doing this, but I will work well, right? Well, we don't want to be slow. So machine learning really parameterizes or encapsulates this function f as some parameters theta. So the theta are your parameters of your model, and they are really a function of the training data set that you created. And mathematically, there is a statistic of the training data set that is sufficient for the purposes of classification. No one is forcing you to learn this statistic. You do this, you learn this statistic in order to be efficient at inference time. Okay. Learning a theta is difficult if I don't give you too much label data, because you will have a very high variance on the estimator. So here is the one trick that you can do. Because at few shot time, you may not have a good statistic of your parameters, you do the search over all these functions more explicitly. Roughly speaking, you train again on the training set at inference time, but you don't know the label of the last datum or the label of the test datum. So let's say if yn plus 1 is the label of the test datum, then I'm solving a problem which is find with the best label y hat, which is the argmin over all possible new classes, yn plus 1, but argmin over an entire minimization over your parameters theta. Your model is again trained on the entire training set to maximize, let's say, the likelihood of your labels. You may want to keep it close to the parameters that you learned at training time. Theta star of ds are the parameters you learned at training time, and that is really what this green term is doing. So ignore the green term if you will, but imagine this entire black business being simply fine-tuning at test time, but fine-tuning while having access to all the training data. Remember, at few shot learning, you don't have a lot of samples. So every little bit that you can glean out of the training set helps you. In this case, we do something drastic. We simply fine tune on the entire training set again. This is a very natural idea, as you can see. This has a name. It is what is called transductive learning. And transductive learning works as follows. So focus on the picture on the left. The positive balls are images from class 1. The negative balls are images from class 2. And let's say if I were fitting an SVM or a max margin SVM, I am interested in finding a hyperplane that splits these 2 points. And it has the largest margin between these 2 point clouds. This is the max margin hyperplane. If I give you some test data, and the test data is shown on the right-hand side picture with these empty circles, I don't know the labels for this test data, but if I give you the test data and allow you to think a little bit, you may want to move your hyperplane from the horizontal position on the left to a little bit tilted position on the right. Because you see, look, a lot of these empty points lie on the positive side, a lot of these empty points lie on the negative side, they are presumably negative, have labels -1. Adapting this hyperplane from the training hyperplane that you created to the test hyperplane is what transductive learning means. It is simply a way of looking at the unlabeled test data and adapting your model. And remember that this is not a new idea. It is actually Wapnick's work from 1996. After he finished working on SVMs, he started working on transductive learning, incidentally. And this is a very commonly used idea when you deploy machine learning models in practice. If I give you 3 test data, I can give you a better answer for all 3 than me being able, forcing me to create outputs or predictions for every single test data without knowing the distribution of test data. That is the difference between inductive learning on the left-hand side and transductive learning on the right-hand side. This is what we do. So here is a very simple algorithm for image classification, few-shot regime. Train a large deep network on the meta-training dataset. So if you have ImageNet, train a standard network on ImageNet, as many classes as your money can procure, and as large neural network as your GPUs can fit. This is a sound thing to do because neural networks are good function approximators. And if you regularize them very strongly, then you know that you're not overfitting on this meta-training set. The second key idea is to initialize a new classifier on top of this network. Typically, when you do transfer learning, you take a pre-trained network and then remove the top layer of this network because it was trained to classify these different classes, and then add a different layer to classify your new classes. We don't do this because in few-shot regime, there are lots of meta-training classes and very, very few-shot classes. You can do very well by simply adding a new classifier layer on top of the logits, instead of throwing away a large amount of information that was learned in the last layer of your original network. So you add a new classifier on top of the new classes. And this has this is a good thing to do based on some theory and recent papers, but it's very natural when you think about it. Now you simply fine tune the network with label data from your new task. And your new task may give you one label data for every category, and you do the fine tuning entirely. You may also want to use some training data to do the fine tuning, but that's fine. Let's say we don't do it for now. This is good old fashioned fine tuning. You can also do transductive fine tuning, where I take the unlabeled test data for which I don't know the answers to, and you ask me for their answers. And I can do transductive learning, let's say by forcing my network to be very confident about one particular class. If I give you an unlabeled test data, this test data should belong to one of the 5 classes that I'm forcing you to classify. It cannot split its logits into all 5. So you say minimize the entropy of the predictions of this network on the unlabeled data. This is what transductive learning would look like in this regime. So a very, very natural and simple pipeline. And there are a few practical tricks that you can always do these days with deep learnings. Let's say you do some cosine annealing of step sizes, the learning rate, to do heavy regularization. You may want to do 16-bit training if you want to train networks very quickly. Remember that in the few-shot regime, you want to regularize these very large neural networks as aggressively as you can, because you don't want the networks to overfit on the meta-training data set. Their real objective is to adapt to the new data. You don't want them overfitted. Here is how it looks as an example. So focus on the crosses are the label data of the new classes. Each color is a different new class. In this, we have 5 new classes. The crosses are the label data that I gave you at test time. The circles are unlabeled test data. And what I'm plotting here are the features of all these images. The translucent circles are the features of the unlabeled test data before I started transductive fine tuning. Okay, so the translucent circle, this purple circle here, belongs to this particular place, but it's really very far from the purple cross over here. So it would get misclassified. It could potentially get classified as a green image class, and you would make a mistake on that data. As you adapt the network in fine tuning, you can see that the support samples or the labeled samples barely change in their embedding. The network knows that these are correct labeled samples, so it doesn't change their features. But the unlabeled data moves. So the purple clouds, purple points now move close to the purple cross. For instance, the orange points here all move down to the orange cross. And now you're getting very good classification performance because this is an orange cloud. All the orange points are close to the orange cloud. So this is how fine tuning looks, or this is how transductive fine tuning looks. You're really forcing this orange dot here to be confident of belonging to only one cluster. It could very well go to the green cluster like this red dot, but it better go to one of them. It shouldn't be undecided. That is what you do in transduction. Let's look at a few results, and I don't want you to read this entire table, but watch my cursor. So on the first column are a bunch of recent algorithms for image classification, for few shot image classification. And they really started in, let's say, 2015 or so. The new papers keep coming up. The 4 columns here are 4 typical data sets that people try to use as evaluation benchmarks for these problems. And support-based initialization is the algorithm that simply trains a neural network on the meta-training dataset and does not perform any adaptation. So it simply performs clustering of the new data given this neural network. And you can see that on some of the datasets, even the support-based initialization, let's look at this line. The support-based initialization is very good. So this number is 75 as compared to 80 of a sophisticated algorithm. If you train the meta-training network well, without any special tricks, with standard cross-entropy training, you are doing as well as some of the other algorithms. If you do fine-tuning with vanilla fine-tuning, you don't even need transductive fine-tuning, you're already better than almost all algorithms out there. If you do transductive fine-tuning, you are ridiculously better than all other algorithms out there. So when this number is, for instance, 68% accuracy, whereas the other algorithms are more like 57, 56, 62. And these are large gaps in performance. Over the last 4 or 5 years, the numbers have gone up from, let's say, 51 to 57. And with basically machine learning 101, you're doing better than these numbers. The key lies in not because we are geniuses at training, but really in creating a very simple algorithm without a lot of moving parts and evaluating this algorithm correctly or well. This one baseline, we like to call it, because it's not an algorithm. This is really a first step at measuring the performance of few-shot learning. So this baseline works better than all existing algorithms for few-shot learning today. And it is very simple to code up. And we've seen similar performance on a lot of different data sets. Let us look at a very large experiment. So this is the largest few-shot learning experiment attempted to my knowledge. This is the ImageNet 21K dataset, 14 million images, about 22,000 classes. And if you think of the distribution of samples per class, the x-axis is the number of classes, the y-axis is the number of images per class, and plotted on the log scale. So there are a lot of images with more than 1,000 classes, 1,000 samples per class, but then the number of samples per class drops drastically. You can imagine that the blue part of the curve is training data consisting of a lot of frequent classes. There are about 7,000 frequent classes, and you can evaluate your algorithm on the green part of the picture, all the classes for which you don't have enough data, and there are about 13,000 such classes. With transductive fine-tuning, or even without transductive fine-tuning, actually, the accuracies on one shot 5 ways, so one labeled example 5 new classes from the green region after having trained on the blue region, are as high as 90%. And at 90% kind of accuracies, these algorithms are, roughly speaking, actually the second one should be one shot 10 way instead of 5 way. At 90% accuracies, these algorithms are basically good enough to be deployed with a few additional practical tricks. So you have good deployable few-shot learning algorithms without even trying, roughly speaking, by simply doing a better job of training on your training classes and a tiny bit of fine-tuning on the green region. I think like the reason people haven't identified such a simple baseline yet is because we've been plotting tables like these in all our papers. No one reads these tables. They only see whether the number that you report is better than the previous numbers. It's very hard to encapsulate all this information together and understand which algorithm is better and which one is worse. So we kind of came up with a way to evaluate few-shot learning. And this really starts from the fact that there is a task is of a certain difficulty. If you give me lots of labeled data, very few new classes, then this is an easy task. If you give me many new classes, very few label data per class, then this is a difficult task. And I would like to kind of come up with a quantifiable metric that puts in this intuition. If you give me a task that is different from my training data, then this should be hard. So we kind of came up with a metric like this in the paper, and I won't go into it right now, but you can read about it in the archive version. The x-axis is what is called hardness. Hardness is how hard a particular few shot task is. The y-axis is a measure of accuracy. So right now, when I showed you the table, I've been showing you 1 point on the purple line here, 1 point on the blue line here, etc. The different colors are different data sets. The purple line is ImageNet, green is, for instance, TRT ImageNet. And I've been showing you really 1 point on each of these lines without understanding how the line looks at all. I want a line on this curve, which is more or less horizontal. So the accuracy is constant. Even if I give you harder and harder classes, of course, that's too much to ask. If you give me difficult classes, you would imagine that the line slopes down a little bit. So what I may be interested in, for instance, is the area under the line for a problem like this. If algorithm A has a larger area under the curve than algorithm B, then I know that algorithm A is better. If you show me 5 different numbers on these 2 lines, I have no way of checking which algorithm is better, because some of them may be larger for A, some of them may be larger for B. But this is really a proposal for more systematic evaluation of few-shot learning algorithms that we would like to kind of explore in the future. Are there any questions on this part before I move to the second half of the talk? Okay, so
Pratik,
the second,
sorry,
yes.
Pratik, before you move on, I just wonder whether you've had any response to this proposal within this community.
Yes, actually. So, and it has been a very good response, I would say. So there are new data sets cropping up for few-shot learning, and people are using both the baseline and the metric. They're still exploring it. So this paper was put on archive about 4 or 5 months ago. So people are beginning to use it, but yes, it is widely recognized that in the meta-learning literature, as also the few-shot learning literature, it is very difficult to evaluate algorithms, both because of the high variance in their performance and because the data sets that we evaluate them on may not be sufficient. This metric, for instance, in fact says that the data sets in few-shot learning are good. The way you evaluate them is not good. For reinforcement learning, we have a similar setup where we came up with the opposite conclusion, that the algorithms, we don't know whether the algorithms are good or bad because the data sets that we train them on are pretty poorly designed. So people are beginning to use these things. How we proceed and how much more quantifiable we can make this business is yet to be seen. That is really where the second part of the talk comes in. So if I wanted to summarize, this is work with Yansong Gao, who is in the audience. We can catch him for more difficult questions. He's a PhD student in applied mathematics. And roughly speaking, the previous part of the talk can be summarized in 1 sentence. Transfer learning is a very good way to do few-shot learning. Of course, there are details. You need to do a good job of this transfer learning. But now you would like to understand how far along can we stretch this? How much can I transfer? Can I always transfer from a source dataset to a target dataset? No, right? So if you train on apples and oranges, you're not going to be very good at transferring to radiology images. So what are the general principles that govern transfer learning? And this is what we would like to understand. So we'll shift gears a little bit. This part of the talk will be quite theoretical, and I will walk you through all the equations that we need to understand. But this is the goal. Let us think of one way in which one may formalize the learning process. And this is what is called the information bottleneck principle, or the information bottleneck Lagrangian, from Naftali Tishby's work in the late 90s. I would like to think of a Markov chain. X is my data, Z is the representation of this data, and Y are the labels. So think of Z as the features of your neural network, and Y are your supervised labels, X are the input images. We say that Z is a representation of data. In statistics, it is a statistic of the data. And we want this statistic to be sufficient. Sufficiency simply means that you can predict Y from Z. If Z was consisting entirely of zeros, then you cannot predict Y from all these zeros. Z is not a sufficient statistic. It is still a statistic, it's a garbage statistic. You want Z to be minimal in size. I want my features to be kind of small if I wanted to store them on the hard disk. And even if you are not interested in storing them on the hard disk, you can show that if Z is small, then you can create predictors for Y that generalize well. And the way to understand this is actually quite simple. If my data X was consisting of images of dogs on green grass as background, if my Z was a representation that spent a lot of energy on remembering the green grass, then every single time I show it a picture of a cow on a green grass, it is going to call it a dog because it overfit on the grass. And overfitting simply means that Z is larger than required. It is not small in size, in information theoretic size or any other size in norm, whatever you please. So we want Z to be minimal. Minimality simply means that, let me go back one slide. Minimality simply means that I would like to throw away information about X. I don't want to remember the grass. I only want to remember the features of the dog. And one way to write this down is as follows. So I here denotes mutual information. I of X comma Z is the mutual information between the data and your representation. You would like to minimize this mutual information over the arrow Z given X, your encoder. At the same time, you would like to maximize the mutual information between the representation and the labels Z and Y. That simply means that Y should be able predicted very easily from Z. This is what is called the information bottleneck Lagrangian. The bottleneck really lies in the size of Z. If Z is too large, then X comma Z is large number and Z comma Y is small. If Z is small, then Z comma Y is good, but then X comma Z is also good. So you want Z to be small. The one thesis I want you to remember from this talk probably is doing well on one task necessarily implies throwing away information from that task. If I want to be good at classifying dogs, I have to throw away information about the grass. And this is exactly the information I may need if my next task was classifying grass. So if you want to think of transfer learning and supervised learning have kind of a tussle between the two. When I'm doing classical supervised learning, I'm interested in throwing away information. When I'm doing transfer learning, I should not be throwing away information because the information that I throw away may be the one that I need to do well on a new task. It's a very simple argument, but that is the crux of transfer learning. And that is exactly the key idea here. So in the information bottleneck minimizes your information. It doesn't let us measure what was thrown away. We would like to measure what is thrown away. How do you measure what is thrown away? This is roughly speaking, comparing what was existing to what could be. So come up with some canonical task to measure discarded information. You could take this canonical task to be anything, but there is a special task called reconstruction of data. If I'm good at reconstructing data, then I am good at solving any other task because reconstruction is the superset of all tasks. If I can recreate data, then I can solve any task that depends on the data. And this is another key point. So reconstruction is kind of a blanket all special task, which forces Z to memorize X completely. And if you compare your performance as a supervised learner to your performance as a reconstruction or an autoencoder, then you necessarily get an idea of what was thrown away by the supervised learner. This is the canonical task that helps you measure stuff. So this is an architecture that we'll focus on. X is the data, Z is the representation, and there is an encoder that goes from X to Z, standard stuff in autoencoders. There's a classifier that goes from Z to Y, which I will denote by C. There's a decoder that goes from Z to the data back, X, and that I will call a D. And the entire name of the game is in understanding how these three models play with each other: the encoder, classifier. This is the standard supervised learning network on the first line, and the decoder that tries to kind of act as a little thermometer on Z to measure what Z is remembering or what Z is learning. And we are going to build a theory that kind of puts these three quantities together on a sound footing. Here is an autoencoder. So the Shannon entropy, most of you might have seen this before. Let's say this is simply measuring the complexity of the data. If your data is very complicated, then the entropy of the data is large. Distortion is a quantity that I'll denote by D. D is a quantity that is the integral over your data, integral over all possible representations Z, but it is a measure of how well you reconstruct the data X. So it is the logarithm of D of X given Z. This is a large number, or distortion is small if you manage to reconstruct data very well. It measures the quality of reconstruction. This is the same as, let's say, JPEG encoder's distortion. There is another quantity which is called a rate, which is simply the number of bits that you use to store Z. Mathematically, it looks like this. It is the entropy of E of Z given X normalized by some other quantity called M of Z. We'll not worry about what M of Z is. M of Z is kind of, think of it as the Lebesgue measure on the space of Z. But this is really the entropy of the output of your encoder. If the rate is large, then that means that your encoder is remembering a lot of information about your data. It may not be good as a classifier. If in that case, the distortion will also be small because it is remembering a lot of information about your data. It will be able to reconstruct the data well. Okay. So focus on these two quantities: distortion, which is, let's say, the L2 error of your reconstruction, and rate, which is the number of bits that you need to store Z. Some of you may have seen a quantity of this form. So H less than D plus R. This is what is called the elbow. It is called the evidence lower bound. And this really is a fundamental bound on the distortion and the rate on one side. H is out of your hands. H is the data set that someone else gave you. So when you minimize or maximize the entropy of the data, I think the inequalities, when you maximize the likelihood of data, you're maximizing something of the form R plus D. So focus on this particular problem here. F of lambda is the minimization over the encoder, the decoder. Let's not worry about M of R plus lambda times D, the rate of your model and the distortion of your model. This is exactly what you do when you fit a model using variation inference today. This is really a relaxation of the fact that if I fix the space of neural architectures and I force you and I tell you that I want a decoder with so and so distortion, D, then there is an optimal value for the rate of this encoder. So the two quantities R and D I have tied together by a constraint that is simply, I don't know the constraint, but I can write it down as R equals some function of D. And what this what this problem really is, it's a Lagrange relaxation of this constraint. Okay, it depends on the parameter lambda, which is the dual parameter to the distortion. Focus on the picture on the right now. So I'm going to plot R and D. This is a cartoon. This is not an experiment. So R is on the x-axis, D is on the y-axis, and focus on the red line. The red line is the space of all possible points that I can reach for different values of my parameters. So I pick a model architecture, I pick a lambda, and I train the model once. I train an autoencoder once for simply R and D. There is no classification yet. I may reach different points on this red line. What you can prove is that there is no way you can go beyond the red line. So you cannot go into this particular region of the parameter space. This is kind of a phase space of R and D. And the red line is a fundamental bound on how much rate and distortion you can tolerate. If you want a very small distortion, you want to be somewhere here on the red curve, you will be forced to have a very large rate. There is no way you will get small distortion with small rate. There is no way you'll reach somewhere here. And the same thing, if you have a very small rate, that means that your encoding is very simple, then you will have a very large distortion. You will be somewhere here. So the RD curve, let us call this the rate distortion curve. This is also seen in information theory. I've just put it into a little more variational terms. It is a curve that joins together R and D. irrespective of the model. So if for given a model, I guarantee you that you'll lie somewhere on the red line. Okay. Now you can kind of extend this Lagrangian to our model. Our model consisted of the encoder, decoder, and the classifier. So I'm going to add another term, which is gamma times C on the right-hand side, where C is simply the classification error of my model. Okay, a classification error I will denote as the log likelihood of C given Y given Z. So this could be the cross entropy loss if you wish. It is exactly the cross entropy loss in this particular case. It could be something else. And now I have three quantities to play with, right? I have R, G, and C. Turns out you can come up with a few other quantities which we are exploring now. For instance, the entropy of the model parameters. This is really a distribution that of your parameters after training on the training data. How many different models fit the same data set? That is what S measures. But let's focus on R, G, and C for now. Just like you have a curve in R&D, you have a surface in RDC. So these are three axes: rate, distortion, and classification. And now I have a surface that I have drawn in this gray region. This surface, you can prove, is a convex surface. And that's kind of very powerful to do mathematics with it. This surface is a surface that understands all the constraints, information theoretic constraints between the three parts of your model. There are places where I can reach. So for instance, if I want a large rate, I need to also have a small classification error and a small distortion. I cannot get large, or the opposite actually. If I want small rate, then I need to also have large classification error and large distortion. The connection with thermodynamics is very interesting, and that we've been exploring alongside this. Thermodynamics, mathematically speaking, is simply a study of continuous surfaces of this kind. Every single time you have a problem of the form this, f of lambda times and gamma equals to minimization over some parameters of some functionals. These are functionals, remember, not functions of theta, because they're information theoretic quantities with integrals and stuff. Every time you have a surface like this, you can define what is called a formal thermodynamics. In this case, these are simply the KKT conditions that I've written down here. dr equal to negative lambda times dg, which is the derivative differential of distortion. dc is the differential of classification, and ds is the differential of entropy. And what this constraint really looks like is the first law of thermodynamics. The first law of thermodynamics says that if I take a mole of gas and perform some thermodynamic process on it, then the energy is conserved across these, the universe. What this constraint really says is that information is conserved across these three quantities. Either my classifier and the encoder throw away information. If they throw away information, the decoder catches it back. And because the decoder wants to be good at reconstruction. So these three different models kind of trade off information with each other. And this constraint really says that just like physical energy is conserved in physical processes in the first law of thermodynamics, information is conserved in this particular architecture for that we have concocted. And that is something very powerful, right? Now you're getting a law out of this construction that tells you something about these three functions. Okay. Let's not worry about this. The surface I want you to understand is that the gray surface is a surface of R, D, and C right now. But there's always the parametric family that lies behind it, the neural network's parameters. One point on this RDC surface, and let's say you started your training at this part, wherever my cursor is, and you train, you're really like falling onto the surface somewhere, depending on what lambda and gamma you pick. So let's say you fall at this point. There are many, many possible neural networks that give the same point on the RDC surface. And what we would like to study, or what we study in this particular paper, is how to travel on this surface. So let's say I give you this point here, how to go from the brown point to the blue point. I would like to design a process that travels on this surface. adapt my parameters of my model in such a way that it travels on this surface. Another key point I would like you to remember is that this surface is a function of what? This surface is a function of whatever architecture I picked, whatever lambda, or whatever architecture I picked, and whatever data that someone else gave me. It is not a function of anything else. It is a fundamental surface up to the architecture and the dataset. And if I change the dataset, the entire surface changes. If I change the architecture, in the sense, if I choose a weak architecture, then the surface kind of comes out like this. So the red line kind of shifts outwards if I start choosing weaker and weaker architectures, and it shifts towards the origin if I choose more powerful architectures. Let's try to define, kind of take the analogy with thermodynamics a little further and define what is called an iso-classification process, just like you have an isothermal process in thermodynamics. Iso-classification process is a process that lives on the surface, but which keeps C constant. So it changes R and D in such a way that C remains constant, okay? And mathematically, you can do this pretty easily. Let's say J is the constraint that defines the surface. I would like to say that I can change my parameters. So the gradient of J with respect to theta is 0 all across the changes to my parameters. And this is simply for telling saying that the changes to my parameters are such, or my process is such that I don't go out of the surface. I can now design a Markov chain Monte Carlo process out of this. I can say that I want to change my parameters lambda and gamma in such a way that I want to go from the brown point here to the blue point here. So I'm changing lambda and gamma from lambda 1 gamma 1 to lambda 2 gamma 2. But I want to remain on the surface. So d by dt of this particular constraint is 0. This is what is called the quasi-static constraint, forces you to stay on the surface. And let's say I want my classification error to not change. So this is an iso-classification condition. You write these two equations down. This will look like a stochastic process, and you can also execute the stochastic process for all neural networks. It is not any harder than training a variation inference model. This is how it looks. So this is a iso-classification process for MNIST for different initial lambda and gamma. Because classification error is constant on the right-hand side plot, this is the validation loss. The rate and distortion are shown on the left-hand side plot. So as you see, let's say that let's pick the blue line of lambda equal to 0.25 and gamma equal to 4. I start at, let's say, distortion equal to 30 and rate is maybe 5. When I execute my classification process, I travel along the green, blue line. And this exactly looks like the RD curve that we saw a little while ago. The classification error across this entire process is constant. So now we figured out a way of traveling on this surface. You can do it for different values of lambda and gamma, of course. An interesting thing that happens, which is actually a pretty deep point, is for CIFAR, when we used a more powerful network, the RD curve is more or less straight line. And this is something that you notice all the time when fitting powerful neural networks with variation inference. The problem with the straight line is that the lambda gamma are almost unchanged across the entire straight line. So the lambda gamma of this particular point is very different from this particular point, not very different from this particular point. So in practice, when you train models with ELBO or you train variation inference models, it is very difficult to control whether the encoder memorizes or the decoder memorizes, because the encoder and decoder kind of throw away information to each other. If the encoder is not doing well, the decoder kind of picks up the slack and starts memorizing. If the decoder is not doing well, the encoder picks up the slack and starts memorizing. And you will see this quite often. So a lot of results, a lot of, let's say, practical results that use variation inference models tend to be overfitted exactly because of this phenomenon, where the two models share information across each other. And that is really seen by this straight line here. We have a slightly different way of traveling on the equilibrium surface that we will not get into, but you can read the paper. The basic idea is that we, instead of traveling on the surface exactly, we kind of hop on the surface and come back. So we do these tiny hops to go from the brown point to the blue point, because going along the surface is too slow computationally. So we do these little tiny hops. Now comes kind of a key point. So the surface is a function of your data set. No one is preventing me from changing the data set during this entire process. So I'm going to take a source distribution, a source data set, which I'll denote by PS, and move it to a target data set distribution, the target data set, slowly. So I'll simply define kind of an interpolating distribution. You can come up with any other transport mechanism, and we also show results with optimal transport in the paper. But this is now a changing dataset distribution on the left-hand side. It goes from the source to the target. You can again define the exact same process now on this changing dataset distribution and execute the process. And notice what happens now. So you have a completely controlled mechanism to transfer representations. If your classification accuracy was 95% on the source dataset, I guarantee you that the classification accuracy on the target dataset is also 95, up to the size of the model and up to the fact that the target dataset is close to the source dataset. But this is a completely controllable way of doing transfer, and you don't have it now. So right now, when we do transfer, we kind of simply try it on the new dataset, and if nothing works, we just go and complain to our advisor, right? In this case, you have a mechanism that allows you to do transfer learning guaranteed, and it comes with guarantees. Here is how it looks. So you take a source task. This is a very simplistic experiment. MNIST digits from 0 to 4, MNIST digits from 5 to 9 is the target task. Focus on the picture on the right-hand side. So the non-equilibrium process, the blue process, is the one that was first trained on 0 to 4 and then simply fine-tuned on 5 to 9, like we do today. Of course, the error on 5 to 9 was very bad when you started the fine-tuning, and as you fine-tune, you kind of reach good accuracies on the target dataset. The green point is the one where you are not training on the source at all, you are training directly on the target. Because MNIST is an easy problem, the green point is essentially the same as the blue point. The geodesic quasi-static process is a specialized isoclassification process that we constructed. I did not talk about it here, but it's an isoclassification process where the data set is changing. It starts with pretty high accuracy on the target task, and this accuracy is constant on the target task. This is beautiful. So this orange line is flat, and that is exactly what the mathematics predicted. dc by dt is 0 as I do the fine-tuning process. Let's look at CIFAR. So CIFAR really consists of two things. It's a data set of vehicles and it's a data set of animals. I think there are 6 animals and 4 vehicles in CIFAR. So the same thing persists. Now you see that the blue line, which is directly training on animals after fine-tuning on animals after training on vehicles, does not reach very good performance because your model was overfitted to vehicles and it did not manage to unlearn vehicles before moving on to animals. So you get, let's say, something like 80% accuracy. The green point in this case is much higher than the blue point. By directly training on animals, you are not hampering the model with this pre-memorization business. And the orange line again is roughly constant. This is what your stochastic process guarantees you. It's nice that the orange line is definitely more than the blue line, higher than the blue line. So you're doing better. It is also higher than the green point, which is really the reason you do transfer learning. You do transfer learning because you want stuff that is better than training on the target data set from scratch. This is kind of the conclusion of my talk. So to summarize, what we showed was that very simple methods like transductive fine-tuning work extremely well for few-shot learning. And the correct way or the right way to understand this, in my opinion, is that neural networks are very powerful function approximators. So when you use them for tasks like few-shot learning, like adaptation, there is a lot of memorization going on in these models, and you need to be very cognizant of how you can exploit the memorization. The memorization, the feature space on the meta-training dataset is very rich, and there is no need to throw it away when you, by training clustering model or by throwing away the top layer when you do fine-tuning. So simple algorithms that kind of exploit this intuition about high quality functional approximators are some of the best algorithms we know today for feature learning. And the same result is, roughly speaking, also true for reinforcement learning. And we have a new paper about it. The second point is that the rate distortion classification surface is a completely fundamental quantity for learning. And that tells you a lot about both the learning process itself and how to regularize the model during learning. It also tells you about transfer, which is what we focused on. But these days we are kind of developing a pack-based version of these ideas, or we have been kind of exploring what is it inside the architecture that makes it good for a data set. This surface helps you understand it. Some architectures are good for some data, some are not, and that presumably has to do something with the curvature of the surface, maybe other kinds of quantities. So in physics, some of you may have heard of quantities like magnetic susceptibility or electric permeability. These are quantities that are fundamental about matter. They are not dependent on the process that acts upon it. On heating the water doesn't change the specific heat of water. And this surface allows you to characterize such invariants for architectures, which is what we have been exploring. And a little punchline at the end, we've been doing very well in the era of big data. Collect me lots of data, fit a neural network, I can launch a company. The next stage is really about how to understand little data very well, how to take machine learning from one specific problem to a million problems with very little data, but which are presumably correlated with each other. You do this when you do personalized learning, you do this when you do adaptation, you do this in almost every problem where you don't want to train from scratch, either because you don't have data or you don't have time. Email all the questions to me, or you can also catch Yansong. So if you want to read more about these things, these are some of the papers. They are on my website. We really talked about only the first and the last one. There are a couple others you can also look at. And I will take questions if you have now, but I think we ended a few minutes late.
Okay, well, thank you very much, Pratik. I think we have time for maybe one or two if people have.
You can also complain if you don't have questions.
This is Kostas.
Yes.
Can you tell us in the final experiment with the MNIST data, if what would happen if you had used the Z only from the autoencoding and you had run a classifier?
That is actually the blue line. So the blue line doesn't.
Okay.
Yeah, the blue line doesn't care about the decoder. It only cares about the encoder and the classifier.
Okay, good.
Pratik, could I ask? This is a beautiful, intriguing, and exciting way to think about, using rate distortion theory. The thermodynamic theory, of course, is really adiabatic and not in steady state, and you're hoping to extend these ideas to the RL setting, which is not necessarily an equilibrium.
Yes,
I'm wondering if this adiabatic point of view would also help you in an RL setting. You really have much more choice over what data to collect, and so your surfaces, you're not settled down to a surface particularly. I'm wondering if you think that this point of view is going to be dynamically helpful, as it clearly seems to be in these steady state batch processes where you have all the data. You're never going to see more data. You don't have any control over what data to collect. I wonder if you're optimistic about that, or whether, one thing at a time, don't worry about that dynamical version yet.
Yes, so that's a very beautiful point. The short answer is that we haven't thought about it. This setting is very specialized to adaptation. It is not an online learning setting. So the surface is not allowed to kind of run away from you. Neither is it allowed to change very quickly. So this is just for the adaptation setting. The way you could, so reinforcement learning, there are different ways you could think about it. You can think about it as an online learning problem. but you can also think about it as an offline learning problem, where I run a controller for many, many times. I collect a data set from this controller, and now I think about how my data set changes when I make changes to the controller. So you could still kind of, at the cost of significant latency, bring down RL to the batch setting. And there are merits to doing this. So a lot of real problems actually look like data that was collected, let's say year 2017, Amazon ran some policy on the cloud. Year 2018, this policy was changed. And no one is allowing me to go and collect more data from these policies, but they are happy to give me data from these 2 years, right? So you can, a lot of real problems in reinforcement learning don't really look like you running policy gradients to collect more data. They may be, you may derive a lot of mileage by simply understanding it as a transfer problem. Of course, there is utility to also doing the online setting, let's say for experiment design, or maybe like exploration kind of problems. But it's kind of a large spectrum. And the problem with reinforcement learning that I personally find is there is a very, very large number of moving parts in RL as compared to supervised learning. So in our group, we've been kind of bringing down reinforcement learning as close to supervised learning as we can by thinking about these offline problems, instead of going into this very vaguely defined regime where all you have is algorithms and no mathematics to talk about them.
So Pratik?
Yes.
I had 2 questions. So beautiful work, like really, really, really nice. I really enjoyed this. So sort of 2 questions about connecting the 2 parts of your talk.
Mm-hmm.
So one of them, you started with very high variance across the few-shot learning, and you were pointing it that was kind of ignored, right, in the community, that there's this high variance. And so one question for you would be, can you exploit some of the statistics, like when you're doing your transductive learning and you're looking at the adaptations or other things, to say this specific task is I'm really not going to be confident about, or this is going to be very hard for me to give predictions, right? So that might be a way to decrease those variance, or at least, especially if you take out the hard parts that you're saying.
Yes, so that's a good point. And you can construct metrics, and we have constructed something like confidence of the classifier on these new labels. In practice, it feels a little funny, right? So this farmer sent me some data. I told him, sorry, I cannot do it. I cannot solve this problem. Go do something else. So while reporting these metrics, so think of it as follows. So every little point here is the accuracy on a given task. I can think about of drawing an ellipse around it, which is the confidence of my classifier. And I can discard the ones with large variances across them and report only the ones with small variances. And that will bring down the error bars. But I think the error bars in few-shot learning are very fundamental about the problem. They are in some sense not even an artifact of the, not even a consequence of the algorithms. It's really about data.
Right, so that leads me to my second comment, right? So if you go back to that slide that you were just showing, right, when you're referring to your hardness, and that's like the measure that you defined, right?
Yes.
So it seems to me that so what you're showing here is across all the data. But if what's going to happen is the hardness is going to highly depend, it's going to be context specific, right? Like you were giving later the example of, I want to classify a cucumber, but I've only seen dogs and cats, right? Because that's very different. So the hardness is going to really depend on what you've seen before. If what you've seen before in your meta-learning is close enough, then you're going to be able, and this image that you're showing here does not capture that. So it would be very nice.
That's
right?
A beautiful
if you can
point.
say, like if you know James Zhao work where he identified influence samples that really influenced my decision on this one. So you could presumably do something at the level of the class to say, this class really gives me what I need to perform well on this, etc. Right? And sort of
So that's a beautiful point again. This hardness does not depend on it depends on the meta training set, but we don't know how it depends. For instance, the hardness actually uses a pre-trained model on the meta training set to evaluate hardness of the test tasks. what we've been doing theoretically along the lines of the second part of the talk is to come up with basically a distance between two tasks. And this distance between two tasks is a function of the distance between them as data sets, as distributions, but it is also a function of the hypothesis class that joins them. So you can kind of define essentially a way how easy it is to go from dataset 1 to dataset 2 modulo along with some notion of how big is your hypothesis class. So we've been studying this in the last, let's say, a month or so. And that is what one would want to come up with if you want to put a metric on the space of tasks. Thank you.
Well, all right, wonderful. I think, why don't we go ahead and thank our speaker? I think this has been an extremely illuminating discussion. I certainly learned a lot.
Thank you.
Fantastic. Well, all right, wonderful. Please keep your eye on our set of announcements for future GRASP talks. And stay well, everybody. Thanks for participating. Great job, Pratik. That was just fantastic.
Thank you.